I'm Brina. My drug is Ditropan. That is the um, brand name. The generic name is oxybutynin. And then highlighted there is the chemical name. It's quite long and difficult to say. Um, Ditropan is used for an overactive bladder. Um, it works by allowing you to, by relaxing your bladder and allowing you to be able to empty your entire bladder when you go to the bathroom. Um, you get an overactive bladder when you aren't able to fully empty your bladder each time you go to the bathroom, and so you're having to go more frequently because you're only partly emptying your bladder. And so, some reasons why you wouldn't take this medication is if you have urinary retention, glaucoma, or gastric disorders, especially motility gastric disorders. Um, Ditropan can have some significant interactions with pramlintide, atropine, antihistamines, and antispasmodics. Something I thought that was interesting about my drug is that it may cause hallucinations, and so it's just kind of fascinating of why some people, in rare cases, get that side effect and other people don't. And it's just kind of, I thought that was kind of a fun fact. Fun fact about my drug is that it may cause hallucinations. So I will draw the line bond or skeletal structure of my drug. Um, so there is first I'll draw a benzene. I love to call it a carbon hexagon, but that's not the the actual term for it. And so my molecule is quite big, so I'll go down. None of the carbon or hydrogen atoms are shown in the line bond structure. So a carbon here will be bonded to an oxygen. There'll be two lone pairs, and that oxygen is bonded to a hydrogen. And then down we'll just do another one of the. Okay, let's retry that. That was not looking too good. There we go. And so then we'll have another carbon, and off of that carbon there will be an oxygen with a double bond to the carbon. And then that carbon will also be bonded to another oxygen. There'll be two lone pairs on that oxygen. And there's going to be a couple carbon bonds here, carbons bonded to other carbons. And then a carbon will be bonded to a nitrogen. There are some hydrogen bonds on here, it's just they're not shown. And then off of that nitrogen, there's some more carbon and hydrogen bonds. So this is a line bond structure of ditropan or oxybutynin. Now moving on, this is the expanded structural formula of my drug. The only difference between this expanded structure and the line bond structure is that all of the carbon bonds and hydrogen bonds are written out. So now moving on to the VSEPR theory molecular geometry predictions. So basically this is just trying to show a 3D version of ditropan. That's what the triangles and dashed lines are trying to show, is that it's 3D, it's not flat. So it's trying to give a more realistic picture of oxybutynin on a 2D piece of paper. And so you'll see in the different colors here, I have the different molecular geometries. All of the blue are trigonoplanar. That means that they're 120 degrees and there's 3 electron groups and coming off of the central atom. And so you can see a couple are 1, 2, 3, 4, 5, 6, 7 of the carbon atoms. The molecules or the atoms around them, they're trigonoplanar. That's the molecular geometry. And you can see there's two bent molecular geometries and around the oxygen atoms. That means that there's 4 electron groups. 2 of them are lone pairs. Then we've got the linear molecular geometry, there's the two carbons in yellow, and that just means there's two electron groups, and that's 180 degrees. It's a straight line. And then there's one trigonal pyramidal molecular geometry, and that's around the nitrogen. There's four electron groups, and one of them is the lone pair. It's around 109 degrees. And then all of the other kind of central atoms left that gray, I'll quick put dots around them. Those are all tetrahedral. That means that there's four electron groups. And that the bond is 100 and about 109 degrees. So let me see, I think I almost have all of them here. I got all of them. So that is the VSEPR model of my drug. Here we have the molecular formula of my drug of ditropan, and that's circled in black. And then we have the molar mass calculation, and so I use the periodic table for that. You can kind of see the math behind it right here. And so my drug is 357.5 grams per mole, and that is the molar mass. And then moving on to this, it's still blurry for some reason. Let me see if I can get that to focus real quick. Okay, well, in the meantime, until that gets to kind of focus, that is just that page is the hydrogen bonding with water. It's just an exercise. It's not my my molecule. It's not ditropan. There we go. Now it's starting to focus. Okay. So you can see with the red dashed lines, that's just where the water molecules are bonded to this molecule. It's just another random drug, I'm sure. And so wherever you can see where I have them labeled as donors and receivers, I'll just kind of be short on this one since it isn't ditropan. Okay, so now moving on to my drug, you can see all of the hydrogen or water molecular bonds, hydrogen bonding with water. And so I have one donor and four acceptors with ditropan. And you can see that just kind of all labeled here. And then the dashed line shows the bond of the water molecules to the to ditropan. Okay, so now moving on. This is polarity and solubility predictions. You can see circled, those are all of the polar bonds. And it's kind of difficult to see, but I have arrows kind of pointing, and I show the delta negative, a little bit of positive, a little bit of negative. And so my molecule, the molecule of oxybutynin, that is a polar molecule. There's hydrogen bonds, there's dipole-dipole forces, London dispersion forces. Those are the intermolecular forces of ditropan or oxybutynin. And so when we're looking at if it's soluble and trying to make predictions, we know that like dissolves like. And so we know that water has hydrogen bonds and dipole-dipole forces, London dispersion forces. And we know that my drug does too, and it's a very polar molecule. It's also, because the polar bonds don't cancel out, it's a polar molecule, and there's also hydrogen bonds. And so we know, and so we can predict that it would be soluble in water. And then you can't really know until you actually do it. But then when I look through PubChem of when people actually did put oxybutynin into water, it is soluble. And then here's just the solution calculations. What we're trying to figure out is if we want 50 milliliters of solution and we want the concentration to be 2.30 times 10 to the negative 2, we want to figure out how much of my solute, how much of my drug in moles that we're going to need. To be able to have that concentration. And so what you're going to do is you're going to add the solute first to the drug, and then you will fill it with the solvent. The solute is the drug, the solvent is water, or, in this case it's water, until the desired amount. The reason why you do want to do it in that order is because you can make sure you get the exact 50 milliliters of solution that you're wanting. And so when you can do all my calculations, I know that I need 1.15 times 10 to negative 3 moles of ditropan to be able to have that concentration and that amount of solution. And then if I want to get the grams, I converted that using, the molar mass, and so we know that we need 0.41 grams of my drug for that solution, that concentration. Now I've been asked to find how many milligrams of ditropan I will be in this in 2.0 milliliters of solution with 3.0% W over V, and that will be 60 milligrams of my drug.